Now we're going to move on to actually looking at chemical reactions, not simply phase changes, but we're going to see that the mathematics is very, very similar. Now, when we do this, we want to be able to decide or determine whether heat's a reactant or a product. For exothermic reactions, remember, heat is listed as a product because it is exiting or leaving the process. It is produced in the process. This means, what this means physically, is the energy required to break bonds is less than the energy that's released when they form. So we're going to have some excess energy remaining. For endothermic reactions, heat is listed as a reactant. And in this case, it means that the amount of energy required to break bonds is greater than that which is released as the bonds formed. So delta H is positive. Now, when we write an enthalpy change for a chemical reaction, it is for that reaction as balanced. So in this particular example, we see that the heat was written as a product. When heat is written as a product, you might want to try these on your own. Pause the video real quick before I give it away. Heat's written as a product in one, and heat's written as a reactant as another. When it's a product, it's an exothermic reaction, and we would say that delta H is equal to minus 220 kilojoules. Now, we don't say per mole in this case. It's implied per mole of the reaction as balanced. Per 1 mole of propane, per 5 moles of oxygen, per 3 moles of CO2, per 4 moles of water. If it was balanced as a different multiple, we would have a multiple of this value. Now in this case, it's written as a reactant. That means it's an endothermic process. And we would write delta H is equal to positive 180.7 kilojoules. That would be per 1 mole of nitrogen, per 1 mole of oxygen, or per 2 moles of nitrogen monoxide formed. Let's see that as well in the next reaction. So, the key is, the take-home lesson from that is when an enthalpy is given, it is for that stoichiometric amount as the equation is balanced. And that's assumed to be with the lowest whole number ratio, unless it is very, very, very clear in the context of the question. So for this reaction, we have 89.3 kilojoules given. It's written as a reactant. That means that much is entering. It's endothermic. We would write delta H equal to positive 89.3 kilojoules. And if we did a little energy diagram, a little sketch of energy, our reactants would be lower than our products. In other words, it takes more energy to break bonds than is released to form bonds. And that's because carbon doesn't exist as discrete carbon. It exists in a network covalent like graphite or diamond or something like that. Now, we'll end up with a variety of conversion factors. It's that many kilojoules, again positive because it's endothermic, per 1 mole of carbon. Now, if we wanted to talk about in terms of sulfur, it's per 2 moles of sulfur, still positive, or per 1 mole of carbon disulfide, still positive. So let's see how we would use those conversion factors in a mathematical equation. This is going to be dimensional analysis. So in that example, we want to know how much heat was absorbed if I had 5.66 grams of carbon disulfide. Well, remember, the conversion factor was plus 89.3 kilojoules was equal to 1 mole of carbon disulfide. So I want to set up a dimensional analysis. I need to go from mass to moles. Once I have moles, I can go to kilojoules. So the strategy is to go mass to moles and then moles to kilojoules. So I've got 5.66 grams. I want to get rid of grams and go to moles. For every 1 mole of carbon disulfide, you can calculate the molar mass as 76.14 grams. Then I want to get rid of moles and go to kilojoules. And my new conversion factor tells me that if I have carbon disulfide, for every 1 mole, it's 89.3 kilojoules. And I would end up with 6.64 kilojoules of energy. Now, before you go on to number 10, you ought to pause the video, try number 10 on your own, try, and then restart the video to get the worked out solution to give you a boost and to see the answer. Now, in number 10, we're talking about the same reaction, but this time we're given an amount of sulfur that's reacted. So now our conversion factor for sulfur is it will require positive 89.3. The sign of the delta H will not change for these different conversion factors. But it's per the stoichiometric amount of sulfur, which was 2 moles of sulfur. So set up your dimensional analysis. I need to go mass to moles, and then I go moles to kilojoules, much like I did before, but the conversion factor is a little different. So I have 16.83 grams of sulfur. Get rid of grams, go to moles. 1 mole of sulfur is 32.06 grams. And this time it's 2 moles of sulfur are required when I'm involving 89.3 kilojoules. So that 2, and of course the molar mass, provide the 2 key differences. And here it would be 23.44, a positive still, kilojoules for the sulfur. Now I'm going to end this clip now, and we will move on to examples 11 and 12. But I urge you to attempt those before you watch the next video segment to see if you